there's like that line.
This looks like an arrow?
Yeah.
Yeah, I buy that.
I don't know. So
And if it looks like an arrow, we can kind of keep on that thought. If you take it and go up, okay, can you see the V there? Okay. And what's the name of that star? Do you remember? Aldebaran. Yes, there's a lot of A's in star names because they came from, is it Arabic? I think so. Okay, so what is that? That's the Pleiades. Yeah, Pleiades, yes. The Pleiades, that's the seven sisters. Does it look like does it kind of look like it has kind of a bowl, like a handle in a bowl? Does it look like a little dipper? And I don't mean to throw anybody off, but sometimes people come to the observatory, they're like, I saw that little dipper, and it's about this big in the sky, versus the little dipper's about, you know, this big in the sky. But through binoculars, okay, here's how it looks like the little dipper. That's the Pleiades, I think through a telescope or a lens, different lens on my camera. Do you see the seven sisters? Remember we talked about kind of objects, I don't know, like in the 1700s there was that Mr. Messier or Professor Messier who was looking for comets. And so we have all these M things. Okay, so this is M45. Messier object 45. The Pleiades, seven sisters, it's all the same thing. And actually, we're going to be looking at the Pleiades. It has, if you look through a better telescope than mine, you can actually get a little bit of nebulosity, a little bit of fog up there. Okay, it's really pretty. And this is one more look at the seven sisters, the Pleiades. Now this one, to me, and we're kind of approaching maybe what you see through binoculars. So
it looks like a question mark.
It does look like a question mark. Very good. Yep. So that is the seven sisters. And a lot of things in the nighttime sky, they look like fuzzy things. You'll be looking like, okay, star, 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 and you're like, oh my gosh, there's something a little bit to that. That's not just a star. That looks like it's got more to it, more substance. And so take your binoculars and look at it and see what you see. So, yeah. All right. Half the lights back on. So, this was kind of about history, okay, kind of building up to what people thought. And I know somebody said those eclipses, would those not be scary if you were back, you know, before kind of scientists understood kind of the orbit of the Earth around the sun and the orbit of the moon around the Earth? That'd be so scary.
Vikings would yell at them.
Vikings would yell at the eclipse?
Yeah.
I can almost see it. "Ah!" Like those credit card commercials, you know. Really? They'd what?
I don't know, I was like, that'd be really weird if they just stood there yelling at it.
Well, they
Yeah.
had to keep Faye from eating the sun.
Well, and then it's kind of like if you have a cold, they say go to the doctor and try to get better. But if you don't go to the doctor, you'll get better. If you go to the doctor, you'll get better. And so maybe they thought what they did made the eclipse go away.
Yeah.
The eclipse is going to go away anyway. Okay. So yeah. This actually just kind of talks you through. Remember we saw the Alexandria Library, which makes people sad? It should make people sad, you know. But we're going to kind of pick up here in the Renaissance time, the year 1453, just the other day. Okay. So I'm going to kind of put some names over here, and I think you had a homework question about this. I'm going to kind of put some names in astronomy, some early names. So Copernicus is the first one listed here. Copernicus. Okay. And the thing about him is he was back to the sun-centered model. Starts with the letter P, but the P is silent. Do you remember kind of how we left with who's the person who was still about putting the Earth in the center, and he had those, he had the planets orbiting the Earth, and he had the kind of the little retro, what do we call them, epicycles of the planets. Just letter P. Do you remember? Yep.
How do you pronounce that?
Ptolemy. Yep.
Ptolemy.
Okay.
He's silent.
So he was Earth-centered. Yep. So basically, it kind of, to me, he was like kind of the last person to do the whole Earth-centered thing. Okay, so we're going to go on. This is like a timeline. So these people actually, there's overlap. These 4 names I'm going to put up here. I think 4, maybe 3. So you see up here, Copernicus brought up the sun-centered thing. The problem with the sun-centered thing, I'll put it down here, is that the church was very unhappy. Okay, the church is happy. Oops, sorry, not smiley face, sad face. Okay, the church is unhappy. Up here, the church is happy. Okay, the church basically wants to keep the earth in the center of everything, which I can't blame them. Okay. Why was the church unhappy? Because we were getting away from, and I'd be glad to talk about my faith outside of class and all that. I am so grateful for my faith.
I will.
But anyway, the church, why was the church unhappy? Because they wanted to make us so very special, and we are very special, and have everything just like, are you the center of the world? Are you that special? And so they wanted Earth to be the center, okay? Now, if we go ahead and make the Earth orbit the sun, we've already kind of removed how important we are, according to the church, at that time. Okay, so that's kind of what we are. So Copernicus kind of brought this up again. Now, he wasn't the first one to go with the sun-centered model. Somebody clear ADs did that, Aristarchus, I think it was. But then, actually, he brought in Tycho Brahe.
He also owned a dwarf.
He also what?
Tycho, he owned a dwarf.
He owned a dwarf. Tycho had lots of money. I kind of think of him as a person with more money than he needs to have. Okay. So the thing with Tycho, he was great with measurements. And I'll show you why. So we needed more measurements to make this whole sun-centered model make more sense. So he owned a dwarf, too. Okay. So I wonder if this is like his dwarf. Oh, my gosh.
He called it Jeb.
He called it who?
He called him Jeb.
Jeb?
Jeb.
I'll have to look into that. But do you see a guy sitting here and a guy sitting there? Okay, or a person standing there. There was no telescopes yet. Telescopes were around, but they were probably just used for navigation purposes. In a minute, I'm going to introduce the word Galileo. That one dude, he actually used a telescope to look at the stars. But actually, though, Tycho Brahe noticed this object. This down here is a blown-up star. This is a supernova, SN for supernova, okay? And then they usually put the year it happened, which I can't remember what year it happened. Oh, there you go, 1572. That's what we call the Crab Nebula, and actually we can still see that today. It won't look exactly like that. It looks like it was probably taken not just invisible, but probably infrared. Okay, but that is the Crab Nebula, and sometimes called Messier Object Number 1, Crab Nebula. So yeah, I'm liking that. What did he call his dwarf?
Jeb.
Jeb. We're going to have to check on that. Jeb, question mark, and there is Tycho Brahe sitting there. Okay. So, let's see. Tycho Brahe, he saw comets, just like Messier was a comet chaser. Okay, the nova down there, he saw comets, and he noticed that comets, one of the thing about comets is that they are transient, and that they're not always there. It just means they kind of come and go. And that was one of the things that the church didn't like either, because if you're going to, now again, we've come a long way, but at the time, it's like, do you dare say anything beyond the Earth's surface is not perfect? Changes is not perfect. Okay, you see comets come and go. I'm like, oh, no, are you sure that's a comet? Yeah. Okay. So you see the next name here. So Tycho Brahe did a bunch of measurements with his fancy observatory, but it was the next guy, actually Kepler, who made a bunch of breakthroughs. So there's a photo of Kepler. Johann Kepler, okay? And he basically, as I understand it, he used Tycho's data. So I will say under Kepler, he was smart. okay? Now, not that Tycho Brahe wasn't smart. I'm sure he was. But it was Kepler that kind of crunched the observations that Tycho Brahe made. So one of the things, and I didn't emphasize it when I was on the Tycho Brahe slide, but one of the things Tycho Brahe watched, and I'll go ahead and put my son back here in the middle, observed, were those wanderers. Okay, remember we talked on Wednesday, and it kind of hurts my brain, this idea that if you look at a constellation, okay, right now, I don't know what Mars is passing through, but you can see Venus and Mars right now. Okay, if you go out the next day, it's going to be moving a little bit, usually westward. The planet will move against the background stars. And that's one of the things that Tycho Brahe made great measurements on. Okay, so he got this direct motion, he got the retrograde motion, he got the direct motion again. And so finally, Kepler put it all together and said, you know what? I'm fine with direct and retrograde motion of planets as long as I go ahead and put the sun at the center and have a few other rules about how the planets orbit the sun. Okay? So like all good scientists, Kepler didn't come up with his 3 laws of planetary motion in a vacuum. He came up with it from observations that mostly came from Tycho Brahe's observations. So I'm going to take a quick look at the 3 laws that Kepler came up with. They're all about, Kepler's 3 laws are all about how planets orbit the sun. And we've actually talked about a few of them already. Okay? His first law, what is the shape? Remember, what's the name for the shape? Starts with letter E?
An ellipse.
An ellipse, yeah. That's his first law. You got that. His second law said that if you're on an inner track, you're going to go faster than if you're on an outer track. We already kind of talked about that, didn't we? Which moves faster in its orbit, Earth or Mars? Earth. Yep, Earth moves faster in its orbit. Yep, that was Kepler's, oh, no, that wasn't Kepler's second law. That was actually his third law. His second law, oh, this one's good too, but I'll show you and then I'll kind of show the slide on it. So is the sun at the center of the ellipse? No, it's kind of off-centered. So if this is, so this is December, and this is when it's closest, right? Kind of December, January, okay? Okay, and when I mean closest, I mean the planet's closest to the sun. And here's where it's farthest, okay? So his second law, okay, basically says that when it's here, and do you remember we called this, and I messed it up the other day, so I'll go ahead and fess up. All right, here's my elliptical orbit, like you guys told me. Here is the sun. We'll go ahead and put it over here at one foci. We'll call this January, okay? I think I called this perigee, but really it's perihelion. Perihelion. I will fess up. Perigee is the moon close to the Earth, and perihelion, sorry about that, is the planet close to the sun. Sorry. And we call this, instead of apogee, it's aphelion. Aphelion. Okay, sorry about that. Okay. So this would be perihelion, not perigee. Okay. And this would be aphelion, not apogee. Okay. I think I was like, but back to his second law. The thing about it is, as a planet goes close to the sun, it goes faster. So it goes, get the idea? So it's the fastest over there and slowest over here. That's it. Okay. All right. So his first law, it's all about the shape of the orbits of the planets. It's about the shape of the orbit of Earth's orbit, and the other planets also have the same ellipse, okay? And the sun is at the foci of their orbits too. So how do you make an ellipse? Well, we talked about ellipses having like foci. It's like a math thing, okay? So I could draw, one of my things, is this you too? I could draw another foci. These are both foci. Every ellipse has 2 foci. Okay, the sun is at one foci. If you're like me, I'm like, well, what's at the other foci? Maybe it's just me. We should write a science fiction show all about what's at the other foci. okay, that we're closer to at aphelion. But anyway, okay, so you can kind of see how do you kind of make an ellipse. You kind of take a string with the same length, and it's kind of like spirograph, and you kind of go around with a pencil. There's the short axis. We call that the minor axis. So this is the minor axis right here. Minor. And then there is the major axis right here. Now, honestly, I never really test over that, but I will say that Kepler had to use that in his kind of describing of his, I think, his last law. All right. One more thing, and we'll be kind of talking about, let's see, let's go back to galaxies. What galaxy are we in? Milky Way galaxy. What's kind of the shape of our galaxy?
Like a disc.
It's like a disc, yeah. There are galaxies that we see that look kind of very circular, pretty circular, kind of face-on galaxy. The more it gets kind of more of an edge on, it becomes what we call elliptical, kind of strewn out. So we can talk about how elliptical is it, okay? And we talk about how elliptical is it by its eccentricity. Okay, if it's perfectly circular, a circle is an ellipse, the foci overlap. So the eccentricity of a circle is 0, okay? And it basically approaches, I think, 1, okay? So you kind of see this is no eccentricity, more eccentricity, even more eccentricity. So in case anybody asks about what eccentricity is for an ellipse. Okay, so just to finish up this is what we've been talking about, and this is my mystery spot. See, I'm just saying, maybe it's not just me. Like, right, okay? So what's at the other foci? So now you can see, I put it on the board to kind of correct myself, but now you see when the planets, including the Earth, is closest to the sun, we call that perihelion, and when it's farthest from the sun, we call that aphelion. There. Okay. His second law, now this is where I kind of moved like that. I went, and then I went out, okay? So it's slow out here, and it's fast. It's slow out near apogee, and sorry, are you serious? It's slow at aphelion and fast at perihelion. And this whole equal areas, all it means is that if I am moving fast here, okay, that means I'm going to sweep out a larger arc. Now, if you take that arc and go back to the sun, we'll call that area A. Out here, you're going slow, so you're going to sweep out a smaller arc. If you make a triangle, in both cases, I'm going to make a triangle, I'm going to call that area B, okay? Basically, this is pretty cool if you think about it. Area A is equal to area B. Equal areas, that's all it is. But bottom line, it goes more slowly out here and faster when it's close. Sounds like a gravity thing, doesn't it? What's that?
Slower over here, faster over there.
Slow over here and fast over there. Yeah. I might have said it
It is
wrong.
gravity that causes that, right?
Yeah. It is gravity that causes that. But at the time, and we're still kind of wrestling with force of gravity a little bit, but at the time, gravity wasn't a thing necessarily. But what scientists do a lot of times is just take their observations and come up with, make predictions based upon their observations. So that's kind of what he did. His last one is my least favorite, and it was the one I mentioned a minute ago when you guys told me that Earth goes faster in its orbit than Mars, and it's a gravity thing too. The closer a planet is to the sun, the faster it moves in its orbit. You'd be like, oh, Mrs. Snipes, I know, but Neptune, like for instance, Neptune way out there, who's Neptune the other day? No, not here? But that cute little blue planet, man, it's got a big old ellipse it needs to, of course it's going to take longer, but it literally travels more slowly in its orbit. Okay. So that's, and I'll let you kind of look it up in case, but that's how I would summarize it. Okay. So, I can't remember dates here, but I'm just going to go ahead and put after Kepler, I'm going to go ahead and put Galileo. How do you spell Galileo? Okay. So, Galileo then kind of came after Kepler, who worked with Brahe, who Brahe worked with Copernicus. So Galileo is a neat story. You can see him holding his telescope. So I'm going to ask you, because I already said the answer to this. Was he the first one to look through a telescope? No. But he was generally the first one to use it to look up. You know, the other ones are also practical. They're trying to get their stuff from point A to point B, you know. So Galileo actually put on his scientific hat, and you kind of see three things right there. Three things that were like, look, Galileo definitely believed in the sun-centered model. Kepler came up with 3 laws of motion of planets as they orbit the sun, okay? And so Galileo was like, let's see what we can do about these 3 objections about this whole sun-centered model. One objection was that if the Earth is moving, then basically, and we know this, like for instance, it's kind of an inertia thing, kind of, okay? If I put this on here, okay, what's going to happen if I move my folder out real fast?
It's gonna have a drop.
It's going to drop, yes. And so he kind of thought that as the Earth moves, okay, all the stuff on Earth should be flying off back in the orbit, okay? So that was one thing that actually Galileo made an argument about that. The other was that the heavens are perfect. Wait, how does this go? From here on Earth, we look out and everything's perfect. So the center of perfection is the center of everything. So, I don't know, everything orbits the Earth, okay? And so what Galileo did is he looked out and he said, no, it was kind of like the comets thing. No, not everything is static. Not everything is perfect. Sometimes what people say is imperfect is really pretty cool. Okay. And then the other one is that, do you guys remember when you hold your finger out and you kind of close one eye and the other eye, and your finger looks like it moves? He said, well, if the Earth is moving, then these stars should kind of scramble. If the Earth is orbiting the sun, then over here, they should kind of scramble, make different pictures, okay? We should see parallax in the stars. And actually, if the star is relatively close, we do see kind of the star moving against the background stars. So he kind of came up with something about that. So here we go. So the whole falling off the Earth thing. He basically kind of came up with an early version of one of Newton's laws. One of Newton's laws. It basically said is if an object is in motion, it's going to stay in motion. And I think that's his first law. I get it mixed up. So bottom line is if I have birds and trees and air, you know, all on the Earth, okay, they are in motion as the Earth moves, okay? So they actually are going to stay on that trajectory with the Earth unless something else stops them. All right. So the whole, you know, the heavens being perfect thing, a couple of things. One is he used his telescope to look up at the moon, and he saw that the moon wasn't like the moon had what people at the time would call, well, I guess they're imperfections. They're pockmarks. Okay. Galileo also saw sunspots on the sun, and I'm not quite sure how he did that. I looked that up one time. I think it might have been either, bless you, I think he might have projected his image from the telescope. But you can't see sunspots without a telescope. So, and he also pointed out remember that M1, the Crab Nebula we saw a minute ago? He said, look, well, I'll just have to tell you it this way. What was so exciting to Brahe when he saw that was if you look at the part of the sky before the star blew up, guess what? No, there was no M1. You look afterwards and it just suddenly appeared, and it will go away after the course of a couple of weeks or so. It will decay. So that means it's not static, not perfect. So, and then the last one, the whole parallax thing. Oh my gosh. Remember I told you, you know, if I go like this, I'm talking about the Milky Way. That's the plane of our galaxy. So another thing that Galileo did with his telescope was to take his telescope and to look, and you should too, with binoculars even, look at the Milky Way, and what you're going to see is it's just billions and billions of stars. It's just amazing. It's just beautiful. Oh my gosh. So the fact that they are so tiny, though, by the naked eye means that they're very far away. So he kind of, and it was kind of like when we did the whole parallax with closing our eyes with one and the other. The farther we get our finger from our nose, the less we actually see parallax. So if you take something and put it far enough away, as we kind of do one eye and the other eye, you're like, oh, it doesn't jump anymore. There's no parallax as I view it from two different positions. There you go. What else did he do? Well, this is kind of fun. Let's see. This one over here is like an image of his scientific journal. The circle is the planet Jupiter, and those little things that look like stars, he actually noted those things that look like stars, and we can see this through a telescope, even my telescope, or the Whitty telescope at the observatory. You can actually see these are actually moons that orbit Jupiter. And so he could actually kind of see a pattern. Okay? And there are 4 moons. Let's see. Sometimes you don't see all 4. Like you see all 4 here. Okay, I don't see all 4. Why wouldn't you see all 4 moons sometimes?
On the other side.
They're hiding on the other side, yeah. Exactly. So actually those 4 moons, where's one? 3, I'll see 4. 10. Those 4 moons anyway are called Galilean moons that orbit Jupiter. So. Then this one over here, this is kind of fun. This is showing you, let's go with this one. This is sun-centered. Okay, sun. This right here, this gray, is Venus. Venus orbiting the sun. Okay, so it goes Mars, Venus, Earth, Mars, blah, 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 blah. So this is Venus, and this is the Earth. Okay, this is the way it is. This is the sun-centered model. And actually, we can see Venus go through phases. I love seeing Venus go through phases. It's so bright in the sky, but sometimes if you look through a telescope, it just looks like the end of a fingernail. It's a crescent, just like a crescent moon. It's beautiful. And this kind of shows you why would you get a crescent Venus? Well, because it's kind of got this sort of configuration. This would be a quarter Venus. Now, over here, can you see Venus? No. Venus would be behind the sun. But here it would be a gibbous and quarter. That is so cool. And this actually, this is the Earth-centered model. This is not the way it is. Basically, if you go this way, Venus doesn't go through phases. So this is the Earth-centered model. No, this is the sun-centered model. Yeah. So he saw phases of Venus with his telescope. So there he is, in all his happiness. I say happiness, but like you can kind of see on the slide, things, and I'm not sure exactly, I wish I knew more about history, but things kind of culminated. Like Copernicus was fine with his coming out with his ideas of basically putting the sun at the center and the planets orbit the sun. Things kind of built up, okay? So when Galileo went to go step out and to publish his findings, which is kind of fun to think about how they did that before, they like posted things on trees and said, hear ye, this is what I believe, okay? And he wrote a book, something published, I think he published it while he was, made limited copies maybe, while he was in under house arrest, basically by the Catholic Church. Okay, and there's like a story out there about his daughter and everything, so anyway. But in 1992, he was finally vindicated. So, I don't know. Anyway, but he definitely published his findings, which supported the sun-centered model of our solar system. Okay. Oops. Go back. There. Cool. So there's a lot of different ways to look at the scientific method of discovery, and I kind of say it's the makes sense sort of thing. I mean, logically, if you have an idea and then you go out and you find things that don't support your idea, you're going to change your idea. And that's kind of what scientists do. Basically, your idea that you come up with would be based upon your observations, okay? And that's kind of what scientists do too. So we observe, or they observe, okay? They come up with how that's happening. They go ahead and sometimes they'll go ahead and publish it. There's a lot of journals, like there's a journal for chemistry, a journal for biology, a journal for psychology. So when you publish it these days, then all the other scientists in that field can kind of look at it. Okay, that's called a hypothesis. Okay, and you don't publish lightly though, because you don't want everybody to make fun of you. Okay, so people will kind of come up with more observations to add to the pot, try to shoot you down. Maybe you'll modify your hypotheses, but if your hypothesis stands criticism, and with your hypothesis you can predict things based upon your hypothesis, then your hypothesis, it's like if you're playing checkers and you get from your side, if you make a piece all the way to the other side, what do you call that? What do you get done? First letter K. King. You get kinged, exactly. And so that's kind of what I think of a hypothesis, is like you find your way through this kind of minefield, your evidence continues to support your ideas, you get kinged. That's a theory. That's a theory. Okay? So when people say it's just a theory, they really should be saying it's just a hypothesis. Then I'd be good with that. But it's just a theory. You're like, no. So anyway, that's one of my things. Cool. This is about the last slide. Yay. Okay. So just in your textbook does this, so I think it's worthy of doing too. It's hard to sometimes these days, especially with the quickness with which we can get information, to kind of sort through what is science and what is just kind of a cool science fiction idea. Okay, science fiction idea. So these are hallmarks of science. Science really needs to only consider natural causes. Okay, only natural causes. Nothing supernatural about it. Gravity is a natural thing. Conservation of energy is a natural thing. Okay. And then the other thing is that you need to be able to test it. Okay. That's a very good test. If you're like a very good to look at to see if it's really science or just something kind of far out idea. You know, like the Earth is round. Can we test it? Yeah, there are different ways we can test it. The other thing is, if you're not in the field, you're like, I don't know if you can or not. And that's where you just need to kind of jump into the field to see if you can test it or not. But if it's not testable, then. And the last one up here is it needs to be as simple as possible. And I told you I was going to kind of come back to this. Do you remember Ptolemy? Bless you. What did Ptolemy think?
The Earth was the center of the universe.
Yep. Ptolemy thought that was the Earth, and this is the sun, and the planets orbited the Earth. Okay. And what Ptolemy did how did Ptolemy explain the retrograde motion of that's the Earth and I'm a planet? How did he describe the fact that the planets go backwards sometimes? Do you remember? Starts with letter E. He kind of, yeah, exactly. I should do like this. An epicycle. Yeah, he did the little epicycle thing. And that's where if you have to try to start to introduce things like those cute little epicycles, to kind of make your observations match your hypothesis, the more complicated you make it, the more likely you're on the wrong track. Okay? So science is generally the most straightforward path possible. If you've ever heard of what does KISS, have you ever heard, my dad used to always say, the KISS method. Do you know what that means? Yep. Keep it simple, stupid. I usually say silly. Yeah, keep it simple. Stupid or silly. Okay, that's the KISS method. Keep it simple. So I kind of finish up with these are not science for one of the three reasons. Okay. Now, do I watch shows about UFOs? Yes. Because I think it's fun. And do I think that people have seen UFOs? Yes. And do I think there might be intelligent life? Yes. Is it visiting us? I don't know. But the thing about ufology, it's like that is not, unless the government releases all their documents, no, I'm just kidding. That is not testable. It's not science. Okay? Astrology is not science. Okay, astrology was the whole, if you do horoscopes, and I do sometimes too, I'm not saying you shouldn't or can't. I'm not saying you shouldn't watch UFO stuff. Okay, it's not science. Parapsychology. Now, the reason these kind of get lumped as sciences is, do you guys know what the word ology means? Very good. Ology means the study of. So it means the study of. And that is kind of, good job, Julian. That is kind of where these things kind of come off as being science, but they aren't. Because they kind of fail at least one of the 3 hallmarks. Okay? Very good. So have a great weekend and hope for clear skies somewhere in there. No more snow.